So back in chapter 1, we first introduced the idea of a quadratic and talked about some of the historical context for where it came from, why people designed things like the quadratic formula, how we can describe properties of quadratics, different things we can look for like roots, and also, most importantly for what we're going to see here, that the graph of a quadratic follows a pattern we call a parabola, that nice U or N shape, depending on certain values that we'll get into detail here. But in that context, we had one main example talking about how the quadratic formula in particular was designed to deal with optimizing the area of a rectangular plot of land given a certain perimeter. And in general, quadratics and parabolas happen to be very good at modeling certain behaviors, certain natural, real-world problems. And that makes sense if you think etymologically, because the word parabola actually comes from Greek, meaning application, where the big application that we have dealing with parabolas and quadratics in the physical and calculus-based world of kinematics is to be able to describe the path, the behavior, the movement of objects that fall or drop or are, for that matter, thrown, because, as you hopefully just saw with my racquetball there, the path that they trace will be a parabola. And in particular, the parabola sometimes is seen to be the inspiration of the title of Pynchon's work, Gravity's Rainbow, where in that he wrote, "But it is a curve each of them feels unmistakably. It is the parabola. They must have guessed, once or twice, guessed and refused to believe that everything, always, collectively, had been moving toward that purified shape latent in the sky, that shape of no surprise, no second chances, no return. Yet they do move forever under it, reserved for its own black and white bad news certainty, as if it were the rainbow, and they its children." Where I haven't actually read Gravity's Rainbow.
Nobody has, but I like the title. It describes the path of a projectile determined by natural law.
More generally, we can think of any sort of dropped path as following something in that nice parabolic quadratic set of behaviors. And that's one of the fundamental relationships between calculus and physics and the physical world, where if you're having trouble thinking of that, just picture in your head a certain shiny red fruit falling on top of a British mathematician and, well, it should start to come together. Where for us, what we're going to focus on for now is what's called the standard or vertex form description of a parabolic or quadratic function, where we have the general function described as f of x equals a times the quantity x minus h squared plus k, where the vertex is at the point hk, and that vertex is the bottom of the curve or the top, that relative maximum or minimum, depending on what goes on with the value a, where, yes, technically we should say a is not 0, but if a is 0, this whole thing's not very interesting because it's just constant, so I'm not going to mention it up there. It's kind of a given, at least in my opinion. If a is positive, then we have something in the family of f of x equals x squared, which we know looks like that. And because we know it looks like that, that's a relative minimum. So we say that this thing will open up. And then if a is negative, we kind of flip that over, talk about those things like reflections from transformations. Then we're talking about it opening down, and thus that vertex would be something like a maximum, where we'll talk more about that sort of thing later when we go back to the idea of optimizing rectangles using quadratics. But for now, we can talk about a general strategy we can use to graph a quadratic function, where what we're going to do is start by determining the direction the parabola opens towards, where if a is positive, it's up, if a is negative, it's down. Then determine the vertex of the parabola, which is going to be that point hk. Then find the intercepts, if they are real, by setting the equation equal to 0. They don't have to be there, but it's nice when they are. Then we find the y-intercepts, in particular, by computing f of 0, we set x equal to 0. And then we plot the points found, where we may need some extra ones depending on what happens, but usually those are enough, by drawing a smooth parabolic curve between them, noting potential symmetries around the vertex. So those are the sort of things we like to pay attention to when it comes to a parabola. Things like where it's symmetric in terms of x or y values. If you have a horizontal parabola, I'm not going to worry about that in this class too much because we like functions of x, but it is technically possible. But we look for symmetries, we look for the vertices, we talk about intercepts. Those are all things that we want to pay attention to among some others that we'll start seeing next with a quick example.